Hello everyone, this is lecture 4 of course PE 645. In the previous couple of lectures, we have covered the meaning of artificial intelligence, deep learning, neural networks, and machine learning. We then went through the radiomics workflow, and we mentioned that it consists of 6 major steps from acquiring the dataset, applying manual segmentation, extracting the features, applying preprocessing, creating the model and training it, and finally reporting high-performance metrics and explaining the decision using explainability frameworks. And then we went through handcrafted feature extraction, and we mentioned that it's categorized under 3 main categories: first order, second order, and higher order. First order deals with the pixel intensities themselves without any relationship between the current pixel and neighbor's pixels. Second order features such as GLCM deals with the current pixel and the neighbor pixels at a specific distance and angle. Higher order features deals with complex mathematical transformations or filters. We covered first order features and how to calculate the different features such as mean, kurtosis, and skewness. And we also covered how to interpret images and to compare between different images based on these features. And then we went through second order features using GLCM. We mentioned that it consists of 2 major steps. The first step is to create the co-matrix, and based on that co-matrix, you can extract the different features such as homogeneity and the contrast before going through other features such as GLRLM and higher order features. Let's work on this project. This project aims and focuses on extracting and analyzing features from a dataset related to Brain Tumor MRI Dataset. And we mentioned that MRI is type of the different modalities such as CT, SPECT, and ultrasound. And each of them, as we discussed, has its specific protocol, pros and cons, and usage. For this dataset, we will get it and then understand the different categories in this dataset, and then we will go through each image and extract the different features such as first order and the GLCM features. And the extraction of these features will require to apply bitwise and between the manually segmented mask and the original image to extract only the ROI, and then apply the bounding correct to extract the cropped ROI, and based on that extracted block or ROI, we will extract the different features from that cropped ROI. After performing that process on all of the images, we will combine all of the features alongside the name of the image and its category or its class in a CSV file, so that in a later phase we can use that CSV file with the machine learning classifier. So let's begin. The dataset is public and shared on Kaggle, and Kaggle is a public platform that utilizes sharing datasets, scripts, and also running scripts. So you can open this link. You will reach to a page that looks like that. You will need to create an account and sign in so that you can download the dataset. Simply press on download and download dataset as zip file. You can also navigate to the details of the dataset in the about dataset section. You can read the different things and how the authors collected or processed this dataset. And also in the data explorer on the right side here, you can navigate to the different folders in this dataset. Inside it, you will find 2 folders. One is called segmentation and one is called classification. In the segmentation, you will find 3 categories. In the classification, you will find 2 categories. In this project, we will focus on the segmentation folder. Let's open the segmentation folder. As noted, you will find 3 subfolders, and these 3 types refer to the brain tumor. You can search for the different tumor types, as we see here, glioma, meningioma, and pituitary tumor on the internet to understand the basics behind each of them. For example, the glioma, they are tumor in the central nervous system, while meningioma develops on the brain meninges. You can go in depth also to understand how it develops, where it develops, what are the different symptoms of each of them. But in our project here, we will consider that each of these three folders are different categories. If you open a folder of these three folders, you will find different images. Some of them are the original images, such as this image, and others are masks. And if you notice here that each image has a corresponding mask with a postfix name underscore mask. So if we have around 1000 files, so you will get around 500 images and 500 masks. So simply, if we can get this image and the corresponding mask using scripts so that we can bitwise and both of them together so that we can gain that ROI, and based on that ROI we can apply grouping so that we can get the grouped ROI and we can extract the different features from that one. Again, we have three folders, and let's assume for now they are three categories for the brain tumor dataset or the brain tumor task, and we have an image and a corresponding mask. The corresponding mask has a postfix underscore mask. We need to apply bitwise AND so that we can get the grouped ROI and apply the bounding rect to get only the region that we need. Then we will apply handcrafted features such as first order and GLCM. After downloading the dataset and extracting it, open the code named Project 01 extracting FOF first order features and GLCM features. Let's go through the code and understand each block so that by the end of this code you can understand how to process a whole dataset and extract the different features from this dataset and store it in a CSV or in a file so that you can use it in a later phase. So in this code, we imported the necessary libraries: OS for path operations, such as creating a folder, concatenating the paths between a file and a folder, CV2 for image processing tasks, such as reading images, TQDM, and this package or library shows a progress bar in loops. So when you run a loop, you will find a progress bar in the command window. NumPy for numerical operations, pandas for data manipulation and analysis, and we will use it to store the data in a CSV file. Matplotlib for plotting images and results, and we will use it to plot the co-matrix and histogram, and the helpers file where we store the commonly used helper functions. First, we define the path of the dataset, and here you need to update this path with the path you extracted the dataset on your hard disk. So remove this line and change it and replace it with your actual path for the dataset. And we defined set of parameters, the distance, theta with 0, and we didn't apply symmetric. We applied normalization, and we applied ignore zeros to ignore the background. Then we added two other parameters, the target size 128 by 128. You can change it to any size, but for this project we will set it by this value to make it a bit faster. But it's recommended to use the actual size of the image, but just for illustration we will downsample and resize it so that the processing become faster. Then we created a flag named doplotting. So if it's true, we will plot the histogram and GLCM co-matrices. So here, if the flag is true, so we'll create a folder so that we can store the different visualizations in it. Then we converted the theta from degrees to radians. After that, we got different classes from the folder. And if you notice here, as we mentioned from a while, that we need the classes or categories from the segmentation folder. So this is the path of the segmentation folder. If you notice here, there are three categories or classes. So this variable will store the three classes. The history is an empty list, and we will use this list to store the different records for the different features. For example, the first image, second image, and so on until we complete all of the records. And we will use it later to convert it to a data frame from pandas and store it after that in a CSV file. We created a loop to iterate over the classes. We have 3 classes, so this loop will be processed 3 times or 3 iterations. We use tqdm.tqdm, and this will create a progress bar. We define here, as we are dealing with a traditional loop, the classes, and CLS will contain the name of the class stored in the classes variable. And we define here a description for the progress bar, so that when you execute it, you will find something that looks like that and the progress bar like that. Then we got the path of the class by getting the original or the main directory and concatenated the class name so that we can get the class path. In the class path, there are different images, including original images and masks. So we got all of the images. Then we filtered out the files that are not masks simply by looping on all of the files and check if underscore mask in the files and ignore it, otherwise keep it. So the files here will be only the original images. Then we created another loop to iterate over these files, and in this case we updated the description called processing class, after that then the class name, and this will create another progress bar. Then we created a variable called file path to contain the path of the image using class path that we defined earlier, followed by the file name. So we will get the path followed by the class name followed by the file. So it will be the absolute or the full path for the file. And then we will get the corresponding mask path by simply replacing .png by underscore mask.png. And this because we mentioned that the mask has a similar name to the image but with a postfix underscore mask. So simply if this is the image name, so you can replace this by underscore.png to get the corresponding mask path. Now we have the paths for the file or the image and mask. We can read both of them, and then we will make a simple check to check that the image and mask are not none, and this means that the application or the script read both of them successfully. Otherwise it will print an error and will skip that image and mask. After that we resized both of them to the target size, and in real applications you can comment these 2 lines so that you can keep the original size for detailed information. But for just illustration, we are resizing the images or downsampling the images so the processing become faster. After that, we ensure that the mask is binary by simply applying threshold function, and this will ensure that the mask is only zeros and ones or zeros and 255 black and white, because some masks may contain grayish pixels and this will hinder the process of bitwise AND. Then we applied bitwise AND to extract the ROI between the image and mask. Then we applied the bounding grid to get grouped ROI. Now we have the grouped version of the ROI. We can then apply the process of extracting first order and GLCM features. To extract the first order features, if you remember, we created a first order features 2D in the helper function that accepts the image and mask, and it should return by the end a dictionary and histogram. So here we accepted the output in 2 variables, first order features and hist2d. We did the same with GLCM. If you remember from the previous lecture, we created 2 functions, calculate GLCM co-occurrence matrix, and that was for 2D, and calculate GLCM features optimized. So we will copy both of them in the helper file. So this will be the first function and it should return the co-matrix, and this is the second function that accepts the co-matrix and it should return the different GLCM features. So here we executed the first function to get the co-matrix, and here the second function to get the GLCM features. Now we have first order features, GLCM features, so we need to combine these 2 features together in a single record, and also we need to attach the file name and the category. So by the end we will get something like a table that contains the file name, the features and the category for each file name or for each record. And this will be the input to the machine learning classifier in a later phase. How to do that? Simply, this is a dictionary. This is another dictionary. So we can simply create a dictionary and combine all of that together inside the dictionary. How? Simply, we need the first column to store the file name. So we created a keyword or a key file name, and we got the file, which is here in the loop. Then we spread and unpacked the first order features using the 2 stars or 2 asterisks. We did the same with GLCM features, unpacked them. So the unpacking process here in Python is similar to getting the first key and the first value, and then followed by the second key, the second value, and so on, until completing the first order features, and the same for GLCM features. So it's like spreading the content in a whole dictionary. And the last column will contain the class label, for example, meningioma or glioma. After that, we will take the all features variable and append it to the history. If you remember, the history was outside the loop, so it can contain all of the records. Then we checked if the plotting is enabled so that we can plot the co-matrix and the histogram. So we will start by plotting the histogram. So we created the path for the histogram and got the min and max, created a figure, created a bar chart, added a title, X label, Y label, and adjusted the layout. Then we saved the figure and declared the current figure. We did the same with the co-matrix. This is the path for the co-matrix. We created the figure, 2 subplots. This is the first, this is the second. The first contains a cropped image, the second contains a co-matrix, and here we created a color bar to show the intensity values for both of them. Then we saved the figure and declared the current figure. If this option isn't enabled, so you will not get any visualizations. After that, we have the history list, which is now filled with the different records, and each record is like a dictionary. You can use pandas.dataframe, and this will convert the list to a data frame. And the benefit of it, this data frame can be stored as a CSV file, comma-separated value file, in short CSV, using the function to_CSV, and it will store it in that path. And you can open it using Microsoft Excel or any alternative application. So simply, the objective of this script is to loop on the different classes and the inner files, get different features, including first order and GLCM, combine all of the records together and store it at last in a CSV or any file so that you can use it later. Once you execute the code, you will find a progress bar, as we noted, using the TQDM package. And after completion, it will complete the first, second, third classes, and it will mention that processing class is 100%, 3 out of 3. And it also shows the time, elapsed time. So for our dataset that consists of more than 2K files, it took around 23 or 24 minutes with a size 128 by 128. If you kept the original size as it is without any resizing, then the time will increase. And as noted, usually we keep the original size and apply the feature extraction on the original size without any resizing or downsampling. In the visualizations folder, you will find for each image, for example, this image, the corresponding histogram and the corresponding co-matrix, and simply using these 2 images and other images from different categories. For example, you picked an image from glioma and another image from a second class, for example, meningioma. You can compare both of them together using the features, or simply you can compare the histogram or compare the co-matrix of both of them. And also inside a single category, you can compare 2 images from the same category. For example, you can pick 2 images or 3 images from the glioma category and compare the pattern of them. So you can say for the first image, it seems to be flattened, or there is a peak, or there is a weird shape of the histogram. or the histogram doesn't follow the Gaussian distribution. And also for the co-matrix, you may say that a co-matrix for a specific image isn't around the diagonal, because some images you will find dots here, distributed all over the co-matrix. And you can validate that using the numerical features by checking, for example, the skewness and kurtosis, and interpret the different values. And if you open the CSV file, which is stored after the completion of the script, you will find the first column includes the file name, and other columns, unless the last one, include the different features from the first order features and GLCM features. And also you will find the category of the different classes, starting by glioma, and if you scroll down, you'll find other classes. So simply, you can pick this image and compare the excess kurtosis and also the skewness for a single category or the same category, or you can pick an image from this category and another from another category and compare and interpret both of them. The aim behind that is to understand how can you reflect on these features as you are a machine learning model. As you are going after a set of lectures, we'll introduce the machine learning model and get this data set and provide it to the model. So we need to understand the extracted features first before applying it to the model. So when the model and the explainability after that says that I could detect that or discriminate between the different categories using, for example, skewness and correlation, then we can validate that yes, we did that using the interpretation before applying that to the machine learning model. So in this lecture, we presented a simple project on how to extract first order features and GLCM features from a public data set. So instead of just applying on a single image, we are now able to apply on a whole data set with different categories inside it. We emphasize the importance of the interpretation after extracting the features, whether you are comparing with between the different categories or inside the same category, because at the end we will present the machine learning model. So we need to ensure that the model is working correctly as intended or as we interpreted the different features.